In the world of cybersecurity, there's this holy grail for hackers, a true ghost in the machine. Today, we're going to pull back the curtain on that ghost, something called arbitrary code execution.
All right, let me just start by asking you a question. What if you could make any computer anywhere in the world do exactly what you wanted it to just by sending it one very specific, very clever message? I know it sounds like something out of a movie, but it's the real idea behind the threat we're going to unpack today. And our story, believe it or not, starts in a really unlikely place. A video game that was almost 25 years old at the time. And it starts with a feat that pretty much everyone thought was completely and utterly impossible. So picture this. It's 2014 at this huge speedrunning event called Awesome Games Done Quick. And a team of gamers and programmers, well, they did something that just shattered the rules of what a Super Nintendo was supposed to be able to do. They managed to program and then play a completely different game. I'm talking the absolute classic, Pong. But it's where they did it that will just blow your mind. Yeah, you heard that right. They did it inside a Super Mario World cartridge. They didn't pop open the console, they didn't plug in any special hardware. They used nothing but a standard controller to literally rewrite the code of the game while it was running, turning it into a totally new game.
And that right there is the central mystery, isn't it? How in the world is that even possible? How can you use a simple controller to inject brand new code into a sealed-off system like a game cartridge? Well, the answer reveals one of the most fundamental vulnerabilities in all of computing.
This impossible feat was actually an incredible demonstration of a concept called arbitrary code execution. This is the ghost in the machine we were talking about, the thing that lets an attacker just seize control. So what is it exactly? Well, the textbook definition is an attacker's ability to run any commands or code of their choice on a target machine. For a hacker, this is it. This is the ultimate prize, total control. Let's break it down a bit more. Imagine you could send a letter to a bank teller, right? And hidden inside what looks like a normal message are secret instructions that make that teller open the vault for you. That's basically AEC. You're sending what looks like normal data, but it's actually tricking the computer into running your secret instructions. Okay, so how does this hijacking actually work? How do you pull it off? It all comes down to a really deep-seated vulnerability in how most computers think, and it centers on this little thing called the instruction pointer. To get this, we gotta quickly look at the difference between code and data. Just think of it like this. Code is the recipe. It's the set of instructions. And data? That's just the ingredients, the information that the code actually uses. Simple enough, right? Well, here's the kicker. Because of a design choice made decades ago called the von Neumann architecture, which pretty much all modern computers use, code and data are stored together in the exact same memory. To the computer, they both just look like a long string of ones and zeros. It has no real way of knowing which part is the recipe and which part is the ingredients. And this is how an attacker exploits that confusion. It's a whole plan. First, they inject their malicious code, but they disguise it as totally harmless data, maybe a username or, in the case of Super Mario, a series of controller inputs. Then, they use a bug to hijack the computer's to-do list, that instruction pointer we mentioned. And all they do is change the address on that list and point it directly at their malicious code. The computer, it doesn't know any better. It just follows the new instructions. Now, getting your code to run on someone else's machine, that's a massive win. But you know what? It's often just the first step. The real goal is to go from being a simple intruder to becoming the full-on administrator of the entire system. See, when you first pull off an arbitrary code execution exploit, you're kind of limited. It only gives you the same level of power, the same permissions as the program you broke into. So if you hijack a web browser, sure, you can mess with that user's files, but you can't rewrite the whole operating system. So of course, they don't stop there. An attacker's very next move is almost always a second attack, something called privilege escalation. They use that first little foothold they got to find another vulnerability, one that lets them break out of their little box and get much, much higher level permissions. And the power difference we're talking about here, it's just staggering. A normal user is stuck in a sandbox with pretty limited access, but an administrator, or what's often called root, has the keys to the entire kingdom. They have total system control. They can change critical files, install whatever they want, and most importantly, they can hide all their tracks. That's the endgame. So, the Super Mario hack is a really fun story, but it's also this perfect little example of a very serious, very global threat. The exact same principles that let someone play Pong inside a Mario cartridge are used in some of the most devastating cyber attacks we've ever seen. Take late 2021, for example. The entire cybersecurity world was just completely shaken by a vulnerability that was described like this: the single biggest, most critical vulnerability of the last decade. I mean, this was a flaw that put millions, maybe even billions of devices at risk. That vulnerability was called Log4Shell. It was found in this incredibly popular piece of software called Log4j, which is used by countless servers all over the world. And it was a specific kind of ACE called remote code execution, or RCE. And all that means is the attacker can run their code over a network like the internet without needing any physical access at all. And look, this was not some isolated one-off thing. These vulnerabilities, they are found everywhere. Log4Shell hit massive services like Apple's iCloud and the gaming platform Steam, but similar flaws have been found in Windows 10, the 7-zip file tool you might have on your computer, even the PHP language that powers a huge chunk of the web. This is a fundamental, recurring problem. Which brings us to this final and kind of scary question. Both the Super Mario hack and the massive Log4Shell crisis, they both happened because of the same core issue. A computer just can't tell the difference between instructions and data. So if that's baked into the very foundation of how our computers are built, can we ever really design a system that is truly 100% secure? It's a question that really defines the entire ongoing battle at the very heart of cybersecurity.